For more physics-related videos, please subscribe. Welcome to Stellar Physics 4G. In this video, I'm going to demonstrate that stars are actually giant freezers. And I'm going to do this by comparing the entropy at the beginning of a star's life and at the end. I've rated the physics level in this video as intermediate. Let's first start off with a picture of the entropy at the beginning of a star's life and at the end. So we're going to compare the entropy during the main sequence phase, which is when a star is fusing hydrogen into helium, which is most of its life, and when it's a collapsing iron-nickel core just before it goes into a core collapse supernova. During the main sequence, let's take a system of 56 protons, so 56 hydrogen nuclei. These 56 protons will eventually fuse into one iron-56 nucleus. In this process, more than half of these protons will have converted into neutrons, but that's not particularly important. What matters is that we started off with 56 free nuclei and ended up with one large nucleus. So initially, this is a high entropy system because there's many ways to arrange 56 nuclei. And remember what entropy is, it's the log of the number of states. So it's essentially a measure of the number of ways a system can be arranged. Since we've gone from 56 nuclei to one nucleus, well, there's really only one way to arrange one nucleus. So as the star fuses hydrogen all the way to iron, it goes from a high entropy system to a low entropy system. Now, entropy is not actually a conserved quantity, but the second law of thermodynamics states that the total entropy of the universe must go up. So, since the entropy in this system went down, at least as much entropy as it initially had must have been dumped out into the universe. And it turns out that the mechanism by which entropy flows out of the star into the universe is through neutrino production. This is because when neutrinos are created, they don't really interact with anything and just leave the star. So now that we have a qualitative picture of how entropy flows from the core of the star out into the universe, let's take a look at how neutrinos are produced. Initially, neutrinos are mainly produced through what's called beta decay. This is when either a neutron is converted into a proton, plus an electron and an anti-electron neutrino, or a proton is converted into a neutron, plus a positron and an electron neutrino. I'm specifying that these are electron neutrinos because there's three types of neutrinos, but that's not actually important for this video. The reason this is called beta decay is because electrons and positrons are also called beta particles. Now remember that I said neutrinos don't really interact with anything, so these neutrinos produced just leave the star and they're basically just energy lost. The number of neutrinos produced through beta decay is not particularly large, and this energy loss is not very significant. Later on in the star's life, when the temperature gets hot enough, neutrinos can also be produced through electron-positron pair annihilation. So how does this work? Photons and electrons inside of a star are in thermal equilibrium, which means they have the same temperature, which means that they are constantly interacting and interchanging energy. I covered this in greater detail in the previous video, Stellar Physics 4F, when I went over the electron-positron pair instability. What's important here is that two photons can be converted into an electron-positron pair, and electron-positron pairs can also be converted into two photons. And because the photons and electrons are in thermal equilibrium, the rates going both ways are the same, which is why I have this double arrow here. There are just as many photons annihilating into electron-positron pairs as there are electron-positron pairs annihilating back into photons. So while there are constantly photons being converted into pairs and pairs being converted into photons, at any given moment, there is always the same amount of photons and the same amount of electrons and positrons, because just as many are converting one way as are converting back the other way. Now this interaction is an electromagnetic interaction. So this does not involve neutrinos, because neutrinos only interact through the weak nuclear force. So there are four fundamental forces: gravity, electromagnetism, the strong nuclear force, which holds nuclei together, and the weak nuclear force, which is responsible for things like beta decay. Electrons in this process are interacting with photons through the electromagnetic force, but they can also interact through the weak nuclear force, which means that while these photons and electron-positron pairs are constantly converting back and forth, once in a while, you get an electron-positron pair converting or annihilating into a neutrino-antineutrino pair. And in this case, I only have a one-directional arrow because the neutrinos are not in thermal equilibrium with the electrons or the photons, because they don't interact with anything. They just flow straight out of the star as if nothing was there. The weak nuclear force is called the weak nuclear force for a reason. It's weak. So this process does not happen very often compared to this process. The rate at which particles are created per unit volume via electron-positron pair annihilation is proportional to the number density of electrons, represented here with n-, since electrons have a negative charge, times the number density of positrons, which have a positive charge, times the cross-section of the interaction. In some interactions, this will be a physical cross-section, but in this case, it's a quantum mechanical cross-section, which you can loosely think of as the target size electron-positron pairs have to hit in order to have a good chance of interacting. And this rate is also proportional to the relative velocity of the electron and positron. I actually derived this in Stellar Physics 1b when I went over the photon random walk. But you can just see sort of intuitively why this has to be true, as well as through dimensional analysis. Now, for both of these interactions, everything is the same except for this interaction cross-section. The cross-section for photons will be pretty close to the Thomson cross-section, which is just a constant. It's about 10 to the minus 28 square meters. The cross-section for neutrinos, it turns out, is proportional to the energy squared, where by energy squared I mean the total energy of the electron-positron pair system. G sub F is a constant known as G Fermi, or Fermi's constant, and it's related to the weak nuclear force. But for the purposes of this video, it's just a number. Since everything else is the same in this interaction, we can get a rough idea on how these two rates, converting to photons versus converting to neutrinos, compare to one another by comparing the size of the cross-section. Now, on average, the energy will be about the same as the temperature. So when we compare these two rates, we get that the cross-section for neutrinos divided by the cross-section for photons is about 10 to the minus 21 times T9 squared, where T9 is the temperature in units of 10 to the 9 Kelvin. Now, I don't want you to take this figure too literally here. This is a very crude back-of-the-envelope estimate. In reality, you'd have to integrate over the number densities and the velocity profiles of the electrons and positrons. What's important to see here is that the neutrino cross-section is much smaller than the photon cross-section. So if we were to take a temperature of 10 to the 9 Kelvin, then T9 would be 1. This would mean that an electron-positron pair would convert into an antineutrino pair roughly 1 time for every 10 to the 21 times they convert into 2 photons. So this does not happen very often compared to this. However, electrons and positrons convert into photons at a very high rate. So this actually does happen. The rate at which energy is carried out by neutrinos will just be the rate at which they're produced times the energy of the neutrinos, which is the same as the energy of the initial electron-positron pair. The number density of electrons or positrons will scale as the temperature cubed. We found this in Stellar Physics 2a and 2b and have used this result numerous times in this series. G here is the degeneracy. It counts how many ways you can put a particle into a given energy state. For electrons and positrons, that's 2, because each electron has a magnetic moment that can either point up or down. So in each energy state, you can put an electron with its magnetic moment pointing up and one with its magnetic moment pointing down. X, which is what we're integrating over, is the momentum divided by the temperature. Epsilon is the energy divided by the temperature. And eta is the chemical potential divided by the temperature. When we plug this into our expression for the energy flowing out of the star due to neutrinos per unit volume, right, this is energy density, so this whole expression is the rate at which energy is dumped into neutrinos per unit volume. And when we integrate this expression over the number density profiles, it turns out that this rate is equal to about 4 times 10 to the 8 times T9 to the 9 watts per cubic centimeter. So where does this T to the 9 come from? Well, the number densities scale as T cubed, and there's 2 of them, so that's T to the 6th. The cross-section scales as the energy squared, so that's going to be proportional to the temperature squared. So now we have T to the 8. And then we multiply by another factor of energy, which means we're multiplying by another factor of temperature. So there's where your T to the 9 comes from. So this rate, which is essentially a rate of energy loss, is highly dependent on the temperature. So now you understand how neutrino production results in energy flowing out from the stellar core and being dumped into space. And what's important here is not so much that they're carrying out energy, which is itself important, but in this process, they are also carrying out entropy. And this is basically what a freezer does. It takes energy and entropy from inside your freezer and dumps it into the room and keeps the food in your freezer cold. If you're finding this video interesting so far, please like and subscribe and maybe share it with a few friends. Alright, so now that we have energy or entropy being dumped out of the star via neutrinos, the question is, how much entropy is lost through this process? So let's calculate that now. I'm going to calculate the entropy per baryon during the beginning of a star's life, which is the main sequence, and the end of a star's life when its center is an iron-nickel core just before it goes into core collapse supernova. For the main sequence, I'm going to simplify this a little bit, and I'm just going to take the star to be a hydrogen maxwell-boltzmann gas. So I'm going to ignore the electrons and the fact that there's also other elements in there like helium and maybe even heavier elements. This will just change the result by a factor of 2 or 3. In this video, I'm only going to care about an order of magnitude result. I actually already derived the entropy for a Maxwell-Boltzmann gas in Stellar Physics 4a, where I found the binding energy of the sun. So I'm not going to rederive it, I'll just take the results from that video. You can always watch it if you want to see that derivation. I'm going to take the density to be about 1 gram per cubic centimeter, the temperature to be about 10 to the 7 Kelvin, because that's the temperature at which hydrogen fuses, and I'm going to take G, the degeneracy, to be 2, because hydrogen nuclei, which are just protons, just like electrons, have a magnetic moment that can either point up or down. So there are 2 ways to put a proton in every energy state. So in Stellar Physics 4a, we found that the total entropy was equal to the number of particles times 5 halves minus this quantity called eta tilde, where eta tilde is defined as the chemical potential minus the rest mass energy of the particle, protons in this case, divided by the temperature. And by the way, normally entropy is in units of K Boltzmann, so here I'm dividing the entropy by K Boltzmann to get a dimensionless quantity. Now what we want here is the entropy per baryon. So that means we have to divide the total entropy by the number of baryons. Well, in this case, all the particles are baryons. So that just means we divide by n to get that the entropy is 5 halves minus eta tilde. In Stellar Physics 4a, we also found what eta tilde was for Maxwell-Boltzmann gas. Now we can plug in 1 gram per cubic centimeter for rho, 2 for G, and 10 to the 7 Kelvin for the temperature, to get that the entropy per baryon initially in the star is about 10. Now let's calculate the entropy inside an iron-nickel core, which we're going to take as a sea of degenerate baryons. I covered thermodynamics of degenerate matter in Stellar Physics 4c, so I'm again just going to take results found in that video. I'm going to take the number density to be roughly nuclear density, meaning that there is 1 baryon in each baryon volume. So basically, we have a bunch of baryons all packed together, touching one another, with no space between them. I'm going to take the temperature to be about 10 billion Kelvin, and in this case, the degeneracy is going to be 4. That's because we have 2 kinds of baryons, protons and neutrons, and each of those has a magnetic moment that can be pointing up or down. So 2 baryons, each with 2 possible states, gives me a total of 4 ways I can put a baryon in a given energy state. In Stellar Physics 4c, we found the following expression for the total entropy of a degenerate system, where x is the Fermi momentum divided by the mass of the particle. This is sometimes called the relativity parameter, and lambda c is the Compton wavelength of the particle. We also have an expression for the number density in terms of x, and we can set that equal to nuclear density to find that x is about 0.3. We want the entropy per baryon, so we have to divide by the number of baryons, which is going to be the number density times the volume, and we can now plug in all the numbers to get that the final entropy per baryon is about 0.1. So, as the star moves from the main sequence to an iron-nickel core, it lost 99% of its entropy. Now, not all stars are massive enough to fuse all the way to iron. Stars that are smaller than about 10 solar masses will not get hot enough to fuse past carbon, and those stars will end their lives as white dwarfs. Now you can calculate the entropy per baryon for white dwarfs, and that will basically be the same as this calculation, except that instead of MP, we'll have A times MP, where A is the average atomic number, meaning the average number of baryons in a nucleus. In the case of hydrogen, A is 1. And since we're getting entropy per baryon, we don't divide by the number of particles, we divide by the number of baryons, which will be A times N. And then you have to plug in what the density and the temperature for a white dwarf is, and when you do this, you'll get an entropy of about 1. So even by the time you get to carbon fusion, you've lost 90% of the entropy. And then you lose 90% of that fusing all the way to iron. But what does it really mean to lose 99% of the entropy? Well, remember what entropy is. It's the log of the number of states. So the number of states will be E raised to the entropy. So for a main sequence star, we can roughly say that there are about 10,000 ways that each proton can be arranged, because E to the 10 is about 10,000. And for an iron nickel core, there's only one state each proton can be in, because E to the 0.1 is pretty much 1. So now you see why, from a thermodynamic point of view, stars are actually giant freezers. During the main sequence phase, the star is an ionized plasma with a temperature of 10 million degrees Kelvin. Initially, the entropy per baryon is about 10, corresponding to about 10 to the 4 ways you can arrange every baryon, or every proton. So right now, let's just pause and think about what we're saying here. At this point, I don't think anyone would disagree with me when I tell you this is a very hot system. But nevertheless, I'm going to further demonstrate this by looking at the energy distribution. If we have an energy bin, so you can kind of think of this as a well, at the bottom here we have low energy, and as we move up we have higher energy. The Fermi energy will be somewhere around here, let's say. For this system we have a maxwell-boltzmann gas, and the Fermi energy is not really relevant. For a maxwell-boltzmann gas, the energy will be distributed like this. So almost all the energy will be well above the Fermi energy, and you might have a few stragglers below it. But what's important to take away here is that all of the lower energy states, almost none of them are occupied. So thermodynamically, this is a hot system because all of the energy states occupied by the systems are higher energy states, and the lower energy states, almost none of them are occupied at all. By the time we get to an iron nickel core, we have a degenerate crystalline solid with an enormously high temperature of 10 billion degrees Kelvin. But despite this extremely high temperature, the entropy per baryon we found was only 0.1, which means that each baryon has basically one state it can be in. Let's take a look at how energy is distributed in this system. In this case, for degenerate matter, energy is distributed like this. Only the lower level energy states are occupied, and you might have a few particles up above the Fermi energy. So this system basically has the lowest amount of energy it can possibly have. If the temperature were 0, then we wouldn't have any particles up here above the Fermi energy, and all of the states below the Fermi energy would be occupied, and the highest occupied state would be the Fermi energy. The fact that the temperature is non-zero accounts for there being a few states occupied above the Fermi energy, and a few just below the Fermi energy not being occupied. So this is why, despite having a temperature of 10 to the 10 Kelvin, this system is thermodynamically pretty much frozen. Because even though we have this enormously high temperature of 10 billion degrees Kelvin, the Fermi energy is so high that in order to excite particles at higher energy levels than the Fermi energy, you need an enormously high temperature, much higher than 10 billion degrees Kelvin. Now, I want to point out that these two Fermi energies are not the same Fermi energies. The Fermi energy for this system is much lower than the Fermi energy for this system. In fact, it's going to be way down here. You probably couldn't even see it in this diagram. So now you understand why I'm saying stars are giant freezers. We have gone from a thermodynamically hot system to a thermodynamically cold system. And when I say cold, I mean pretty much as cold as you could possibly get. And we've lost almost all of the entropy. So this is what your freezer at home does. It takes energy entropy from inside the freezer and dumps it out into the room, thereby cooling the inside of the freezer. However, in the case of your home freezer, the entropy will drop by maybe 1%, whereas in this system, it's dropped by 99%. So not only are stars giant freezers, but they're the most powerful freezers in the universe. And the center of a collapsing core, despite having a temperature of 10 billion degrees Kelvin, is thermodynamically the coldest place in the universe. If you enjoyed this video, please like and subscribe, and click the bell to be notified when further videos are released. In the next video, I'm going to start a new chapter covering the various stages of nuclear fusion, starting with the basics of nucleosynthesis. Thanks for watching.